So we're going to do a little more practice with finding inverse Laplace transforms. We've seen this done in some of our previous work last week, and then also in a previous video example. Those ones mainly dealt with inverting linear, where we had linear factors in the denominators, and also maybe where we had to work with partial fractional decomposition to break up a rational expression into its partial fractions. Just to remind you, from this first video on an introduction to Laplace transforms from James Sousa, what the process is, and we saw that in that example one I did in previous videos, that we're taking a differential equation, we're going to take the Laplace transform using some other facts along the way to then get an algebraic equation in terms of the Laplace transform, which we're then going to isolate and then use inverse Laplace transforms to recover the original function. And that's going to help us solve differential equations. So that last part is an important one for us. All right, so we need to be good at doing that. Now, we've already had some experience with examples that are going to turn out to be related to first order equations. We're going to now try to get to some examples that are going to be related to some second order differential equations. And just to remind you, what did we see in one of the last videos is we derived the Laplace transform for cosine of omega t and sine of omega t. And notice for cosine we get s over s squared plus omega squared. For sine of omega t we get omega over s squared plus omega squared. So the common thread between those is that the denominator is the same, the numerator is different though. It's s, the variable s for cosine, it's the number omega for sine. Alright, so let's keep that in mind when we're doing these examples here. Alright, so looking at that, I'm just going to write that on this page here, that we have for cosine of omega t, it's Laplace transform. Again, I'm just going to not put equals. Let's just put an arrow between. And again, thinking about these are related via the Laplace transform. It goes to s over s squared plus omega squared. For sine of omega t, it's related to omega over s squared plus omega squared. So some of these are going to be very straightforward and very simple. For other ones, we might have to do some manipulation to get it into that form of the expression in terms of s that we have on the right hand side there. Alright, so the first one we have in this list is pretty direct. It's definitely a cosine. Just keep in mind here that this is s squared plus what's omega is 2, right? Because 2 squared is equal 4. So thinking about inverting this, what does this go to via the Laplace transform or its inverse? What function of t is this related to? This would be related to cosine of omega t, which is 2t in our case. Okay, likewise here, we can see that omega is 3 for this problem. We have s squared plus 3 squared. So what would this one be related to? This one would be related to sine of 3t. Okay, likewise for the third one, pretty straightforward. Since 1 squared is equal 1, we have omega being 1 there. That would be related to just sine of t. Alright, now the ones coming after this are a little bit more interesting, but they're all, in the sense that they're a little bit more challenging. So for instance, we have s squared plus 16 squared there. Now, what's that going to fit into the mold of? Well, it doesn't have s on top, so it's not going to be related to cosine. It's got to be related to somehow a sine, but for it to be related to a sine, we have to have omega squared in the denominator and then omega in the numerator. So our job is going to be to here force in the omega to show up in that numerator. Alright, so let me just say how that's going to go, and then we're going to see that related to some of the problems we've got after that, the examples after. Alright, so this one, what we have in our denominator is s squared plus 16, which is 4 squared. Now, what we really want on top there is a 4, but we only have a 1. So we need to put a 4 there. Alright, so we're going to need to get a 4 on top of that so we can realize that that's the same as, or that's going to be related to sine of 4t. Now, I can't just put a 4 on top there. We're multiplying the top by 4, so we'd have to multiply the denominator by 4 also. That's equivalent to saying multiplying by 1/4. Now those two quantities are directly equal to each other, or exactly equal, and now we can use that. Alright, these two things are related via the Laplace transform to what? Well, the 1/4 is a constant that will come along for the ride, and this is exactly related to sine of 4t. So those kinds of manipulations are going to become commonplace when we're using the Laplace transform to solve certain initial value problems. All right, let's go and do the next few examples here to finish this off. So looking at this one here, 5 over s squared plus 4. Well, what is omega in this case? Again, it's always s squared plus omega squared. So if we're thinking about that as something squared, it's going to be 2. Well, that means we would want a 2 on top, not a 5. So what we want to do for this one is manipulate that a little bit. We want to definitely say that this is 2 on top over s squared plus 2 squared. But I can't just do that because we already had a 5 on top. Well, we could push the 5 off in the front. That's fine. And then to compensate for multiplying the top by 2, we'd have to multiply by 1/2 or divide by 2. And now that will give us what that's related to. So the 5 times 1/2, we could rewrite that as 5 over 2. And then we know that 2 over s squared plus 4 is the Laplace transform of sine of 2t. Okay, so again, if you want to use the inverse notation, you might see that done in some of the videos. You'd write it like this. The inverse Laplace transform of 5 over s squared plus 4 would equal 5/2 times sine of 2t. I just prefer to draw the arrows and indicate, all right, via the Laplace transform or its inverse, these two functions are related. The function of s is related to the function of t and vice versa. All right, these last two examples are a little bit of a combination of both sine and cosine, and that's going to appear in some of our work also. So let's do that one there. Negative 5s plus 7 over s squared plus 9. Alright, so for this one, we don't just have an s term on top or a numerical term on top. We have both. So what we're going to need to do is treat this as one factor in the denominator, and we're going to divide that up into both the s term and to the 7 term up top there. And that'll give us negative 5s over s squared plus 9 plus 7 over s squared plus 9. Okay, now this one is going to be related to the second term is going to be related to sine. The first term is going to be related to cosine. For the first term, pretty straightforward. We can just pull the negative 5 off and rewrite that as negative 5 times s over s squared plus 9. For the next one, what do we want there? Well, we want to have a 3 on top because 9 is equal to 3 squared. Again, I can't just put a 3 there and delete the 7. We would have to move the 7 factor in the front and then also divide by 3, so that would be equivalent to having 7/3 in the front. So what do these things translate over to? Each one of these terms via the Laplace transform. Notice I'm not writing down equals, I'm writing down, okay, they're related via the Laplace transform to what? The first one, the negative 5 is going to come along for the ride. That one's related to cosine of 3t, and then the 7/3, that factor will come along, and then that's related to sine of 3t. Okay, so it's possible in some of the examples we're going to solve that we end up having to do a split like that for some of the problems. Alright, so for the last example, let's look at that one. That one's going to be similar to the last one we just did, and then we'll have to split it up a little bit. It's s plus 1 over s squared plus 3. Okay, so copying that example down, we had s plus 1 over s squared plus 3. Now we'll do the same kind of split we did in the last example. We'll divide the s squared plus 3 up into both of these terms. I'm leaving that second term off, just, well, I'll put it in, and then we'll divide that up into the 1. And then once again, we need to do some manipulation. What makes this one a little bit different is that we don't have a perfect square in the denominator. Keep in mind here that this is really s squared. If we want to write this as something squared, it's got to be the square root of 3 squared. So that's what our denominator is going to be. So omega in this problem is not an integer, it's the irrational number, the square root of 3. Alright, so now for this first one we're fine. We don't have anything to do. It's just s on top. That's no problem. For this one, because that's going to be related to cosine. For the second one, we want to make the number omega show up on top, so we need to get omega to show up there. And again, like our previous work, we can just do that by insert that factor up top by dividing by the same thing. Okay, so what is this related to? And what is the second term related to? Via the Laplace transform, we end up getting cosine of the square root of 3t, square root of 3 times t, and then plus 1 over the square root of 3 times sine of the square root of 3t. Okay, so again, we did these examples because we're going to be applying these same manipulations when we solve initial value problems. That's the kind of the key step at the end to invert to recover the function of t.